Hi, it was just Mr. Lim here again, and this is our fourth video in equilibrium about the reaction quotient. All right, so let's have a look. So we're going to be learning about the reaction quotient and how it's related to the equilibrium constant, and they are very similar but subtly different. Okay, so describe the reaction quotient. So the equilibrium constant expression, which is what we learned in the last video, right, is a way to show the ratio of reactants to products or products to reactants. Okay, so that's the equilibrium constant expression, which gets you a number. Okay, at equilibrium, so when the two reaction rates are equal and the concentrations of everything isn't changing, the concentrations of these reactants and products, if you put them into the equation, will produce a number which is effectively K. This is our K value for that reaction. Okay, we just learned that in the last video. Okay, at equilibrium. Okay, that's the important part. Okay, however, you can put in the concentrations of reactants and products into the equation when the system is not at equilibrium. Okay, so if you just take a time when the system is not at equilibrium, and then you put in the numbers, the concentrations of all of the stuff, the number that you get will not match the equilibrium constant value. Okay, so you take the same equation, which is the concentrations of products over the concentrations of reactants by the power of their coefficients. If you take that equation and put in the concentrations of reactants and products when the system is not at equilibrium, you get a reaction quotient. Okay, so when you calculate that ratio of reactants to ratio of products to reactants when the system is not at equilibrium, you are solving for the reaction quotient. That's what I just said. All right, so ratio of products and reactants not at equilibrium. The value of the reaction quotient, so the reaction quotient value compared to the equilibrium constant value, gives an indication about which reactions are occurring to bring the system to equilibrium. So let's just have a think about what that actually means. All right. Say you have a reaction A plus B goes to C. Okay, and let's just assume that all of these are gases, right? And I'm not going to put coefficients in there. So therefore the K value, or the equilibrium constant expression, would be C, concentration of C, over the concentration of A multiplied by the concentration of B. All right, and let's just say at equilibrium at 25 degrees Celsius, because remember it's affected by temperature, it's like 80. Okay, however, this reaction quotient, if you were to do this when it's not at equilibrium, we give it a Q at 25 degrees Celsius when it's not at equilibrium, right? You take that same equation, C over A multiplied by B concentrations, but it's not at equilibrium yet. It might be 40 when you put those values in at that instant in time, at like time, like 20 or something, 20 seconds before it can reach equilibrium, right? And this difference in the value is effectively saying that it's not yet at equilibrium. Okay, so let's see what that means then. So what does that mean? That means we can look at those two values, the 40 and the 80, and determine which way the reactions are going. Okay, so let's have a think. If we've got this 40 to 80, the difference there is 40, but the idea is that it's actually lower than the equilibrium constant. If it's lower than the equilibrium constant, that means that at this particular time frame, there are more reactants because the value is lower because it's lower, so you got more of those and less of the products. More reactants, less products than at equilibrium, right? Which means that you need to make more products, less reactants. Okay, so that idea of saying that I need to increase the value, how do I increase the value? I make more products and less reactants. Okay, so let's have a look here. A reaction quotient which is lower than the equilibrium constant, which is just what we went through, so lower than the equilibrium constant, indicates that there are more reactants and less products in this system than there would be at equilibrium. Hey, I just said that. All right. This means that the system has yet to establish equilibrium, so equilibrium is not yet established, and is currently going to make more products than reactants to bring the value up to the equilibrium constant. This means that the forward rate of reaction is occurring at a faster rate than the reverse rate of reaction. Okay, that's because you're making more products. That's why the forward rate is occurring faster than the reverse rate. Okay, if you have a situation where the reaction quotient is higher than equilibrium constant, therefore you have everything as the opposite. You have more products and less reactants, which means that the system is again yet to establish equilibrium and is currently making more reactants than products to bring the value down. So how do you do that? You have the reverse reaction occurring faster than the forward reaction. Okay, so this reaction quotient, same equation as equilibrium constant, it's just that the number that you get is when at a time when it's not at equilibrium, and that value that you get you can compare to the equilibrium constant and say which way the reaction is going, right? It's just useful for working out which way things are going and remembering that not all systems are at equilibrium. All right, that's it. We're going to move on to the next video.